So here we can see an example of a displacement time graph, and there's a couple of key properties that you need to remember. So the first of which is that the gradient is the velocity, because velocity, measured in meters per second, is the rate of change of displacement per second. Well, rate of change, that sounds a lot like gradient. So if we took, for example, the gradient here, well, it's going to cross 2.5, so that's our change in x, and then up 4, so that's our change in y. It's actually our change in displacement and our change in time, but if we work it out, so change in y over change in x, so 4 over 2.5, that's 1.6 meters per second. So the gradient of any any displacement time graph is the velocity. Okay, so a steeper line also means a greater velocity. So if I draw a line there, well, without any sort of calculation, we can straight away say that this line, they were traveling faster at this point than they are on this line. Okay, because the gradient's clearly steeper. Another good thing to remember is points like this, where we've got a horizontal line, means they're not moving, so the velocity is 0. You can sort of figure that out on your own, because you can see that the displacement isn't changing, so they're not getting further away from the origin, they're not getting closer, but time is increasing. So time's going by, they're not moving at all, so velocity must be 0. So another important thing to remember is that displacement and distance are two very different things. So displacement is a vector, which means it has magnitude and direction. So this is a vector, which basically means if we have sort of a running track here and I run this way, well, we're taking this direction as positive. So let's say I've ran 100 meters. Okay. And then I run all the way back. Well, I've ran back 100 meters, so I've ran 100 meters to the right, which is our positive direction. Take away 100 meters to the left, which is negative. That's why we're taking it away. So my displacement would be 0 meters, whereas my distance, which is just a scalar, so scalar, it just has magnitude, is how far I've traveled in total. So I've traveled 200 meters. If I've ran 100 meters out, 100 meters back, I've traveled 200 meters, so my distance is 200, but my displacement will be 0 because I'm back at the origin. So the good thing to remember is displacement is a vector, which involves distance and direction, whereas distance is purely the distance from the origin without a specified direction. So here we can see an example of a velocity time graph, and there's a couple of good things to remember about these. The first of which is that the gradient is acceleration. So you can sort of figure this out without being told it, because a gradient's a rate of change, isn't it? So if we took the gradient of this, it would be the rate of change of velocity with respect to time. Well, that's acceleration. Acceleration is the rate of change of velocity with respect to time. So, for example, if we work out one of the sections, let's take this bit here. So what's that point? Well, that point will be 4. The reason I know that is this has gone up 5, this has gone across 5 there. Here it's gone up 3, so it must have gone across 3. So 1 to 4 is 3. So this bit, it goes across 2 and it goes up 2. So taking the gradient, changing y over changing x, 2 over 2, well, that's 1. What would our units be? Well, I've done meters per second over seconds. So use your rules of indices. This becomes ms to the minus 2, which we should know is acceleration. Okay, so very important that you remember that the gradient of a velocity time graph is acceleration. So if the graph is increasing, then the object must be accelerating. So in this case, it's getting bigger, so it's accelerating. If it's decreasing, like this one, then it must be decelerating. And the easy way to see that is because if we calculate the gradient here, well, change in y, it's gone from being at 2 to being at 0. So it's minus 2. In terms of time, we've gone from 10 to 13, so that's 3 seconds. So we do minus 2 over 3. Well, we can change it to a decimal if we like. So that's going to be minus 0.6 reoccurring. And again, using the logic that we did here, meters per second. So this is negative, so it's decelerating. Okay. A very important thing to remember as well is that the area under the graph is the distance travelled. So working out the area under here, we knew it's at 4. So this bit's too wide and it's too tall. It's a triangle, so we'll do a half times 2 times 2, so we get 2. And then think about your units. You're doing meters per second times by seconds. Well, -1, this effectively has the power of 1. Those two would cancel out, leaving you with just meters. So this is 2 meters. So in this section, they traveled 2 meters. So good thing to remember, but you can always figure it out by just thinking about the units on each axis. Remember, velocity should be in meters per second, time should be in seconds. So another thing to be careful about when adding areas under a velocity time graph, so you might want to do that to find the total distance travelled, is that if the velocity is negative, then the object is heading backwards. Okay, so its displacement will decrease, but the distance will increase. So displacement is not too bad, because displacement, if we just worked out the total area here, that would straight away give you the displacement, because of course you would have a positive take away a negative, and displacement, the negative takes into account the direction. Working out distance is a little bit more tricky, so let's work out the displacement and the distance over these sections. As we said previously, this point is 4, so working out this one, well, just the area of it to start with, it's 3 tall and it's 3 wide, so we would do a half times 3 times 3, so that's 4.5, and because we've done velocity times time, that's going to be meters, so that also comes back from speed equals distance divided by time. If you do speed times time, you get distance, don't you? So 4.5 meters. Then this one, it's 2 wide, 2 tall, so you do a half times 2 times 2, half times 2 is 1, times 2 is 2. So our total distance travelled is 2 plus 4.5 is 6.5 meters, whereas so that's distance, whereas our displacement is a little bit trickier, because notice this bit here, the velocity is negative, so we would actually have to do 2 take away 4.5, and we get minus 2.5 meters for displacement. So you can see, even though we've considered the same sections, we get 2 very different answers. So it's important to be careful considering when the velocity is negative, because you'll end up with 2 very different answers for distance and displacement, and ultimately you'll get the answer wrong if you don't remember that fact. So forming Suvat equations from a velocity time graph. You might look at this graph and think there's not a whole lot of information there at the moment, but we can actually figure out all of our Suvat variables from it. So there's a couple that are quite easy. Well, t straight away starts at 0, ends at 5, so t is 5 seconds. You can read that one straight off. What about u? Well, again, that's just the velocity at the start, so our initial velocity, that's starting from there, so -1 meters per second. You can see we've got 2 already. What about v? That's the final velocity. Well, that's just this point here, which we can see is at 4. So that just leaves us with a to find and t to find. A couple ways that we can do that. First of all, acceleration is the gradient. So think about change in y over change in x. So change in y, that goes up 5, this goes across 5. So we would do 5 over 5, that's 1, and then we've effectively done meters per second divided by seconds, so meters per second squared. You could also use a Suvat equation here because you already have 3 variables. So you could have instead done v equals u plus at, and then we could have 4 equals -1 plus 5a. So then you would have 5 equals 5a, a equals 1. Okay, so I've just noticed I wrote an extra t there, it should have been an s. So the other variable that we don't know is s. So how can we figure that out? Well, s is the displacement. So 2 options here. We can figure out the area under the graph, or we could use Suvat. Let's first do it via area under the graph. So we know the gradient is now 1. That makes this point 1, 0. Okay, so I'm going to work out the 2 triangles separately. The reason for that is because this bit is negative, so that will actually be taken away from our positive section because we're talking about displacement. So this triangle should be relatively easy to work out. It's 1 tall and 1 wide, so it's just half times 1 times 1, so 0.5 meters displacement in that section. Remember, that's going to end up being negative in the end because the velocity is negative in that section. This one's a little bit trickier, but it's 4 wide and 4 tall, so we're just doing a half times 4 times 4, So that's 8 meters. So our final displacement is going to be 8, take away 0.5, so 7.5 meters. As I say, you could also do this via a Suvat equation. So initially we had T, we had U, we had V. We want to figure out S. Well, then we can use S equals a half U plus V times T. Sub in the variables that we know, well, quite nicely, it's all the variables on the right-hand side. So we'll do S equals a half U, which is -1, plus 4, because that was V, and then times by T, which was 5. So working this out, -1 plus 4 is 3. So it's a half times 3 times 5. So it's 1.5 times 5. So it's 7.5. And as luck would have it, they're exactly the same. So you can see now we have all the variables. So we have S is 7.5. We have U is -1. We have V is 4. And we have A is 1. And we have T is 5. Just quickly add some units to those. So meters per second squared, meters per second, and meters. You can see we've got all of them. 2 different ways to do it, but we can acquire all of our Suvat variables from a velocity time graph.